For the problem 8, we are first asked to find the expectation of xt, where xt follows the Poisson distribution. And for Poisson distribution, if x is equals to k, we have its formula equals to e the power of minus lambda times lambda the power of k divided by k's permutation. And based on the property of n distribution, the summation should be equals to 1. So we have the sum from 0 to infinity is equals to 1. And if we rearrange this formula, we have the summation from 0 to infinity lambda power of k divided by is equals to e the power of lambda. And to calculate the expectation, we have to know the summation of 0 to infinity k times the formula of distribution. So how to obtain this k here? So we just take the derivative of this formula on both sides. We take derivative with respect to lambda, and we get that the summation of 0 to infinity k lambda power of k minus 1 divided by k is equals to e lambda. And this form we can directly or obtain the expectation of e based on this formula. So it should we have this term, and this term, and this term just mass and lambda, and we should plus times this term to the right side of this equation. So we get our expectation is equals to times lambda, which is equals to lambda. So but here we have x is actually a function of t. So the expectation of x should equals to lambda times t. And this is for the problem A. And I will make it smaller. And for the problem B, we are asked to find the autocorrelation between T1 and T2. And since from the question we know that if T1, T2, and T3, T4 are non-overlapping, they are independent. So here we have actually a two interval, which is T0 to T1 and T1 to T2, and they are non-overlapping. So the random variables are independent. So we just plug in the formula and we get it is expectation of xt1 times xt2. And we can rewrite xt2 to be, here is the trick, we can rewrite xt2 to be xt2 minus xt1 plus xt1. and we expand this formula, we get it is equal to expectation of xt1 times the expectation of xt2 minus xt1 plus the expectation of the power of xt1. We can separate this term and this term because they are independent, as I stated above. They are a non-overlap region. And so we need to calculate the expectation of the power of xt. And how to calculate it, and based on the formula equation 1 we get from problem A. If we again take the derivative of equation 1, take derivative with respect to lambda on equation 1, and we get that the summation from 0 to infinity k to the power of 2, this is equal to lambda times e to the power of lambda plus e to the power of lambda. And so, and the expectation of x the power of 2 is equals to the summation of 0 to infinity of this power k, the power of 2 of k times the formula of the distribution function, of the density function, and it is equals to times, and again it should also times lambda, and equals to lambda times lambda plus 1. So this is for the random variable x. So for the random variable x with respect to t, we got it is equal to lambda t times lambda t plus 1. And I will make this part smaller. And to obtain this equation, we know from A, we know this part, and these two can be separated also, and this we have calculated here. So we can write this equation to be lambda times t1 plus times lambda t2 minus lambda t1, and plus lambda t1 times 1 plus lambda t1. And after we simplify, and this is based on the assumption that where t2 is greater than t1, and after simplification we got our equation to be lambda t1 times 1 plus lambda t2. And similarly, for t2 smaller than t1, we just swap the position of t1 and t2, and we get it's to be lambda t2 times lambda power of 2 times t1 t2. And for the general case, we got that this should be lambda times the minimum of t1 and t2 plus the lambda power of 2 times t1 and t2. And this is for the problem 8.